Right, the second half of the rates chapter involves what can we do to make our reactions go faster. Now this is a pretty important consideration in industrial chemistry where your obligation is to make lots of product quickly to return value to your investors. So speeding up the rate of reaction is a very important thing in chemistry. How do we do it? Well, basically what is required is to get particles to collide and break bonds more often. So that means they've got to smash into each other hard enough to break bonds. They need to collide with sufficient energy to overcome the activation energy barrier. More collisions which break bonds mean a faster reaction rate. That's the essential connection that we need to make in this topic. Now, you can't just talk about more collisions because it's the quality of the collisions which has to improve as well. So it's got to be more collisions which break bonds, more fruitful collisions, successful, effective, productive, some way of talking about those collisions which have got enough energy to break bonds in the reactant molecules. Sufficient energy to overcome the activation energy barrier. That's a key phrase that you'll be writing out a few times. Now, orientation is also important, especially in organic reactions. So if we look at the addition reaction between ethene and hydrogen chloride, then there's only one orientation which is going to have a reaction occurring, which is going to have bonds breaking. And that's when the hydrogen of the HCl crashes into the double bond between the carbons. That's what breaks bonds. If you do any other orientation, so say the chlorine hitting the double bond, or the hydrogen bumping into another hydrogen on the ethene, or the chlorine bumping into the carbon, whatever, nothing's going to happen. It's got the wrong orientation to break bonds. Got to have the hydrogen bumping into the double bond. So orientation is important. It's just a factor that we need to remember. That's about as far as we take it here. So we're going to be looking at getting more successful collisions. And four main ways that can happen. First way is increasing the surface area. Now, as you should know, if you have small pieces instead of one large lump, you've got a higher surface area, and the logic goes that means more particles exposed at the surface, therefore a higher frequency of collisions between the reactant particles and the surface. So powder explosions are a classic example of that. Powdered aluminium versus an aluminium can. Powdered aluminium is quite explosive. And even flour compared to a lump of starch, a slice of bread. Flour in flour mills, if it's really dusty and there's a lot of flour suspended in the air, flour mills can actually blow up quite destructively and kill people because of that surface area effect. The increased surface area of the starch means once it starts burning, it burns explosively. So the calcium carbonate, this is a classic example. You'll come across this in questions quite often in this topic. It's a classic example of rates. So we can have our calcium carbonate being small pieces, powder even, or we can have it being large pieces. Now if we've got the same mass of calcium carbonate and an excess of hydrochloric acid, what we can do is measure how rapidly the reaction is going by measuring the volume of carbon dioxide produced, how that varies over time. Now whenever you get one of these graphs, a graph in physical chemistry, always look, what are the axes measuring? What does that actually tell us? Well, this graph tells us two things. It tells us how fast the reaction is going. So the pink graph, which is the small pieces, is producing hydrogen more quickly. The volume of carbon dioxide increases more quickly, therefore we've got a more rapid reaction rate. For large pieces, the line has got a more gentle slope, lower surface area, slower rate of reaction. The other thing one of these graphs tells us is the final level. What this is telling us is that at the end of the reaction, i.e. when no more carbon dioxide is being produced, we've got exactly the same volume of carbon dioxide. That means all the calcium carbonate is reacting in both cases. We've got the same amount of product. That's as you would expect in this scenario, but it's always something we need to just be aware of. So the two things you get out of one of these graphs, and this is a classic example of smaller particle size, faster rate of reaction. Now, the question that pops up, how would we measure the rate of reaction in this case? How would we measure what's going on? Well, here we can see volume of carbon dioxide. Are we going to measure the volume of gas produced? Well, not in my lab, because gases are a total pain to deal with. There is a much simpler way. Just think about what's going to be happening if you chuck some calcium carbonate into a beaker of HCl. What's going to happen? Carbon dioxide gas is going to be produced. What happens to that gas? It escapes into the atmosphere. You can measure how the mass of the beaker decreases, because the reason why it decreases is because it's losing carbon dioxide. Second way we can increase the rate of reaction is to increase concentration. This is a pretty simple one. Higher concentration, or higher pressure if we're talking about gases, it's exactly the same thing, means more particles in the same volume, more frequent collisions. So here's one where it is simply the frequency of collisions increases, and it's pretty obvious. Now, the big factor that's going to increase the rate is increasing the temperature. And this is the one where you need to be a little bit careful with your explanation. Average kinetic energy increases, causing particles to move faster. That's what temperature is, basically. It's a measure of the average kinetic energy of the particles. So, temperature goes up, particles move faster. That's going to have two effects. They're going to bump into each other more often, of course, but more importantly, they're going to bump into each other harder. More collisions, a higher proportion of the collisions are going to have sufficient energy to overcome the activation energy barrier. Enough energy to break bonds. That's the key to this effect. Now, a graph of particles versus energy shows this pretty clearly. This is known as the Maxwell-Boltzmann distribution. Thankfully, we don't have to worry about the maths behind it. But what it does, again, whenever you see a graph, pay special attention to what's on the axis. So here we've got number of molecules, so how much of the gas, and here we've got the energy. So what do we see? We see that some particles have got low energy, some particles have got high energy, but most of the particles are somewhere near the middle, somewhere around the average energy. So we see that spread of energies of particles in any sample of a gas. Some have high energy, some have low energy. Now, activation energy is a measure of how much energy is needed to break bonds. So if the particles are moving fast enough, they're going to have enough energy to break bonds. They're going to be over that activation energy barrier. And at low temperature, there's only a small proportion of the gas molecules which have enough energy to break bonds, which are moving fast enough to react. If we increase the temperature, the average energy of the gas particles increases. So we shift the distribution of particle energies to the right. So this time, the average energy is higher. We've still got some particles with a very low energy, but we've got more particles with a high energy. We've got more particles that are over that activation energy threshold. So more collisions are going to break bonds. We're going to have a faster rate of reaction. And that's the key linkage. Adding a catalyst. Catalysts are substances which by definition speed up a reaction, so they're going to work to increase the rate. Key thing about a catalyst, of course, is that it isn't consumed by the reaction, so it's not a reactant or a product. Now, industrially, they're principally metals, and metals with a high surface energy. Biologically, of course, enzymes are catalysts. Biological catalysts are amazingly more effective than the crude things that humans come up with, but they still essentially function in the same way. So we can look at homogeneous catalysts. That means they're in the same state as the reactants. So if you've got a gas phase reaction, like decomposition of ozone, and you've got a molecule which catalyses it, which is also a gas, that's a homogeneous catalyst. You can also have heterogeneous catalysts, which are in different states. And most of the industrial reactions we look at have heterogeneous catalysts. So sulfuric acid production, it's vanadium pentoxide, which is a solid. Production of ammonia, it's iron, which is a solid. They're the ones that we deal with. Nowhere near as good as biological catalysts, of course. So what do catalysts do? Well, they provide a different way to get from the reactants to the products that has a lower activation energy. So they reduce the activation energy because it's easier to break the bonds. Now note that they reduce the activation energy, they reduce the height of that initial hill, but they don't change the final level. The products are still the products, have got the same enthalpy as before, so delta H doesn't change, only the activation energy. It's a very important fact. And we describe it that catalysts provide an alternative reaction pathway. So we're not doing exactly the same intermediate steps when we use a catalyst, but it's the final product which is the same. So looking at our Maxwell-Boltzmann diagram again, so we've got our distribution of particles. The activation energy without the catalyst is fairly high, so only a small proportion of the particles have enough energy. If we add a catalyst, we need less energy. So a greater proportion of particles are above that threshold level. We haven't changed the shape of the graph, the distribution of particle energies. Still got the same proportions of particles at each energy level. It's just that we don't need as much energy, so more particles are going to happily react. Solid catalysts, generally substances with a high surface area, which bind the reactants molecules to the surface of the catalyst, and that makes it easier for the bonds to be broken. And the Haber reaction of ammonia does that. The nitrogen and the hydrogen stick onto the surface. That makes it easy for the bonds to break. If you've got it at 500 degrees and 400 atmospheres or something. And once the bonds break, of course, the product molecules can happily go off. So with a catalyst, we're going to seek to have a high surface area to absorb more particles. That will make it more effective. And just remember that idea of an alternative reaction pathway, which with different steps in the reaction. So now have a go at those questions, submit them on Google Classroom, and when you do so, I'll email out a solutions video.